Okay, welcome to presentation one on graphing. Interpreting graphs. Frequently, an investigation will involve finding out how changing one quantity affects the value of another. The quantity that is deliberately manipulated is called the independent variable. The quantity that changes as a result of the independent variable is called the dependent variable. The relationship between the independent and dependent variable may not be obvious from simply looking at written data. However, if one quantity is plotted against the other, the resulting graph sometimes gives evidence of what sort of relationship, if any, exists between the variables. In laboratory investigations, you generally control one variable and measure the effect it has on another variable, while you hold all other factors constant. For example, you might vary the force on a cart and measure its acceleration while you keep the mass of the cart constant. After the data are collected, you then make a graph of the acceleration versus force using the techniques for good graphing. The graph gives you a better understanding of the relationship between the two variables. There are various relationships that occur frequently in physics. Types of graphs that you'll see in physics class in this course is generally going to be a linear graph. A linear graph is a graph that will allow you to draw a straight line through most or all of the data points. So here's an example of a data table. We talked about position time data tables before. So position is generally the dependent variable, and it's plotted on the y-axis. Time is considered the independent variable, and it's plotted on the x-axis. So here is the resulting graph for this position time data. Notice that the graph goes through 0, 0. It doesn't always have to do that. And the points line up nicely in a straight line. And so we can draw a line through all of the points. This shows a linear relationship, meaning as time increases, position also increases by a constant amount. Line of best fit. Experiments conducted usually result in quantities that do not change by equal amounts during each time interval. A best fit line is a smooth curve or a straight line that most closely fits the general shape of all of the points. So here you can see points that are plotted. This could be position time data or it could be something else. The points don't line up perfectly in a straight line, but generally speaking, you can see that as you move across the x-axis, the points move up in a linear fashion. So a scientist would look at this and say that there is definitely a pattern here. The pattern looks like a linear relationship. And so the reason why they don't line up perfectly is because in a lab, as we talked about before, there's always some error. So they're not going to be perfectly lined up in a lab scenario. But if they're close enough, you can draw a line through the middle of the points and they should touch as many points as possible. And you should have an equal number of points above and below the line. So you can see here we have 1, 2, 3, 4, 5 points above the line and 1, 2, 3, 4, 5 points below the line. And the line touches exactly 3 points. So the line is going through the middle of most of the points. So this is what we call a line of best fit. The line is drawn through the middle of the points. An equal number of points should be above and below the line. The relationship between the variables can be expressed by the line equation. So you should have learned this in math class. A straight line on a graph is expressed by y equals mx plus b. So that's the relationship between the two variables, y and x, where y is the value for the dependent variable and x is the value for the independent variable. B is the point where the line intersects the y-axis, and M is the slope of the line. Slope of the line can be calculated as rise over run or delta y over delta x. If the y-intercept equals 0, then the equation reduces to y equals mx. Steps to plotting data in physics. So 1, identify the independent and dependent variables. 2, choose your scale carefully. Multiples of 1, 2, 5, or 10 are usually acceptable. Make your graph as large as possible by spreading out the data on each axis. Your graph should take up as much of the page as possible. Let each space stand for a convenient amount. For example, choosing 3 spaces equal to 10 is not convenient because each space does not divide evenly into 10. Choosing 5 spaces equal to 10 would be better. To avoid a cluttered appearance, you do not need to number every space. 3, all graphs do not go through the origin 0, 0. Think about your experiment and decide if the data would logically include a 0, 0 point. For example, if a cart is at rest when you start the timer, then your graph of speed versus time would include the origin. If the cart is already in motion when you start the timer, your graph would not include the 0, 0 point. So it depends on the data. 4, plot the independent variable on the x-axis and the dependent variable on the y-axis. So usually you're doing position time graphs. Position goes on the y-axis and time goes on the x-axis. Then plot each data point. 5, label each axis with the name of the variable and the unit. Use a ruler, darken the lines representing each axis. 6, if the data points appear to lie roughly in a straight line, draw the line of best fit with a ruler and a sharp pencil. Have the line go through as many points as possible with approximately the same number of points above and below the line. Never connect the dots. Just hold your ruler straight and draw the line as a straight line across the ruler without connecting each dot. If the points don't form a line but form a curve, then draw a best smooth curve. Lastly, title your graph. The title should clearly state the purpose of the graph and include the independent and dependent variables. Characteristics of a good graph: size. It should take up most of the graph paper with only one graph per page. Title. This should be meaningful and representative of the experiment. Position versus time is an acceptable title for a position time graph. Both axes should be labeled with units. Both axes should have an appropriate scale, and a line of best fit should be drawn. Slope calculations should be shown on the graph. Do not have more than 2 or 3 digits in the number, and you should have an equation for the line, units, and vertical axis intersection. This represents the relationship between the two variables in the experiment. The slope is very important and usually represents a concept. For position time in the next presentation, you'll see that the slope of a position time graph represents speed. That concludes the presentation. You can move on to the second presentation on slope.